Okay, thank you, everybody, and those who are still on live stream. We're moving into the second panel. Again, I would like to thank Headworks for hosting the break. And after this panel is over, you're welcome to stay in the entry and continue your conversations. Those of us who are on the workshops will move on to the smaller rooms. I'd like to introduce Gerald Seidel, who is the co-founder and senior vice president of Headworks International, and he heads sales and marketing departments and directs the engineering team's research and development activity. He holds a number of U.S. and international patents for water treatment, equipment, and processing, and his expertise is in developing new markets and has established Headworks as a market leader in the United States and enables the company's expansion into the Middle East, Africa, South America, and Asia. He's been an active member of the Water Environment Federation since 1994 and serves as an honorary consul of Austria for Texas, Oklahoma, and Arkansas. He's earned his master's degree in civil engineering and has specialized in water and wastewater plant design. And so thank you, Gerald.
Good morning again. I'm honored to moderate the next panel, especially in this building where we are. If you look at the lobby and see all the portraits of the many famous leaders, each of them was instrumental in events or decisions who influenced or changed the course of the world. Therefore, I really urge you all here in this room, let's try to make a difference as well. Very briefly about our company, as Headworks, we provide high-end water treatment solutions for municipalities and industries. With my wife, Michelle, who spoke earlier, I share a passion for the world, and instead of taking the easy route to just concentrate on the home market, we're proud that we have installations in over 40 countries in all continents, and all of them, at the end, improve the basic life of people. Just give you a very brief example. We have inlet screens which protect large pumps from clogging in a river intake in Mumbai, in India, and therefore that changed that finally 5 million people have continuous water 24/7. We upgraded wastewater plants in Egypt to improve the effluent quality from unusable to irrigation reuse quality. And this in a country which today increases the population by 1 million every 6 months, so they need desperately more clean water. In general, the goal of us, like many others in our industry, are to deliver high-end quality which reduces the maintenance needs, reduces the contact of staff with contaminated wastewater, and greatly increases the life cycle costs efficiency for municipalities. For the panel we talk today, I'd like to outline some of the challenges and opportunities we will discuss. In my opinion, we live in our industry in a divided world. We have the developed countries, where we are here. We refine standards and treat water to an even higher level. We have to deal with water scarcity, and reuse becomes a critical issue. On the contrary, on the other hand, some cities like Berlin in Germany face nearly the opposite problem. They are so efficient in water use that they have not enough water in the sewer system and create sedimentation, which creates another problem. We look into energy recovery. A wastewater treatment plant becomes a resource recovery facility. However, this is in itself still not a monetary feasible solution, but sure one of the trends of the future. On the other hand, then in developing countries, they have very different problems. The basic challenge is to provide potable water to people at all, provide a sewer connection to households. In many slums, it's impossible to have a piping system established. We need to develop alternate systems, like the Gates Foundation and other funds work on such developments and support it. Multinational companies from Unilever to Mars or Pepsi-Cola, they apply corporate governance and Western standards, even places where they could get away with a much cheaper solution. Partly, this also has to do with the pressure of media reports of abuse and disasters and the raising public awareness in the Western world, like we saw with the iPhone and our previous speakers. This becomes really a changing world in this regard. As technologists in this industry, our biggest challenge is developing and implementing solutions that address all these problems cost efficiently and technically sound. These solutions are there. The implementation is many times, in our opinion, the challenge. If a city says, come back when you have 5 years of proven experience and successful installations, this makes it impossible to drive this industry forward. It's one of the big challenges we often face. So let us now start our panel discussion, and it's a pleasure to introduce the first speaker, which is Lauren Stadler. Let me introduce her very briefly. She's assistant professor in civil and environmental engineering here at the Rice University. As an assistant professor, she's studying sustainable biological wastewater treatment processes. Lauren's research focuses on advancing water reuse and energy recovery from wastewater using a multidisciplinary approach that combines microbial ecology, environmental chemistry, and sustainable assessment. Prior to joining Rice, she received her Bachelor of Science in Engineering from Swarthmore College and a PhD from the University of Michigan in Environmental Engineering, where her research was focused on understanding the impact of I lost it.
That's all right.
So here, our first speaker, Lauren Stadler.
All right, thank you for that introduction. It's a real pleasure to be here today and to really kick off this panel. We're switching the focus a little bit from talking about flooding to talking about resource recovery and water reuse. And I guess water reuse really comes up in response to a very different extreme event, which is drought. And so when we see really the most movement in terms of water reuse projects, it's usually in response to extreme drought. But I think these extreme events are linked. And when we talk about improving our infrastructure, we need to improve them for both extreme flooding, but also times of extreme drought. Okay, so my goal is really to just give an overview and introduce the concept of water reuse and talk about different approaches for achieving it in an urban setting, and really contrasting some more centralized approaches to more decentralized approaches. Oh, that worked. Okay, so first of all, what is water reuse, just to make sure we're all on the same page? And this is the practice of using treated wastewater for beneficial uses. And so we often interchangeably use these terms, reuse water, reclaimed water, and recycled water, but they're really all referring to the same thing. So don't be confused by this different terminology. And really, it's treated wastewater for beneficial purposes, whether that is potable water or non-potable water, so like irrigation water. So what are the main factors that are driving water reuse? First, of course, like I mentioned before, water scarcity. So these are things like drought, stresses on our water supply, such as population growth and being able to supply the water needs of a growing population, especially in our major urban centers. This is increased needs both for our municipal sectors, our industrial sectors, and agricultural demands. So that's a little bit less relevant in our urban settings, but there's a huge demand for irrigation water, especially in Houston. That's putting stress on our water supplies. And then there's also this desire to move away from dependence on single sources of water supplies. So we get the majority of our drinking water right now and potable water from surface waters from Lake Houston and Lake Livingston. We also get a fraction from groundwater. But in order to diversify our drinking water sources, we might want to consider alternative water sources such as treated wastewater. Another motivating factor is the fact that in many regions across the country, there's more stringent standards for wastewater discharges. So we put our wastewater back into the environment after we treat it, and a lot of the environments that we put this wastewater in are nutrient sensitive. And so as we increase the standards associated with the quality of the water that we put into the environment, that causes we have to upgrade our treatment plants to achieve those standards, and that has a financial burden on these plants. Another argument is that perhaps reusing water could be a more energy efficient means of achieving both potable and non-potable water sources than our current practices of treating surface and groundwater. And this has to do with the fact that we, in addition to spending a lot of energy treating our water and wastewater, we also spend quite a bit of energy distributing it. So if we can treat our water close to where we need to use it, to the standard that it's needed for that use, we could potentially have system-wide energy savings. And then finally, environmental protection. So this is the idea of conserving our freshwater supplies and really improving the protection of our aquatic environments where we discharge our wastewater right now. So one of the major challenges that always comes up when we talk about water reuse is public perception. So people don't love the idea of toilet to tap, the fact that we're essentially going to be potentially drinking or coming in contact with water that was previously wastewater. And this has stalled a number of water reuse projects. And I would say that what this means as engineers, as planners, is that we need to really do a better job engaging the public in these water reuse projects and educating the public and understanding potential unknown risks associated with water reuse. And I would also say that even though we might feel squeamish about the fact that we might be using treated wastewater either for drinking or for irrigation, the reality is that we're basically already using treated wastewater. And many Houstonians are aware of this and many are not, but a lot of our water is basically wastewater that's been treated from Dallas. So Dallas discharges their treated wastewater into the Trinity River. It spends about 2 weeks coming down, ends up in Lake Livingston, and approximately 50% of the lake's water over the course of the year is made up of treated wastewater from Dallas, is the estimated amount. So whether you like it or not, we're already doing water reuse. We're already using that treated wastewater. We have an environmental buffer, yes, but that is wastewater that we're using as a drinking water source. And the reality is that planned water reuse systems are on the rise. There's a lot of water reuse activity going on in Florida and California, and they're really leading the way. But we also have a number of planned projects in Texas, and these water reuse projects are growing. So I don't think it's a question of, is this going to happen, or are we going to do it? But it's kind of when and how, what's the best way? How do we plan these projects in a way that makes them financially viable, environmentally sustainable, and socially acceptable? And so what I want to introduce is the fact that these water reuse projects, can really range in terms of their scale and size. And this can be from centralized projects to more decentralized projects. And so when I talk about centralized, it means that the water is collected and treated in a centralized facility. And I would say most of our cities in the US have very centralized water and wastewater infrastructure. We transport our water over long distances so it gets to our homes, and then we put our sewage into a sewage collection system, and that gets transported to our centralized wastewater facilities. But you can also imagine that a decentralized approach could be potentially much more sustainable from a systems perspective for water reuse. And that's because if we can reduce the amount of distance that we actually have to transport and collect this water, we could potentially save energy associated with the pumping and transport of this water. So collect the water close to where it's produced and use it close to where it's treated. And these projects can range in size. So I would say like a city scale project that's very centralized might be supplying our drinking water with treated wastewater, versus on the other end at the building scale, you can have a smaller scale building that collects its own wastewater in its basement, treats it, and reuses it for irrigation on its own property. And we also think about this scale of centralized to decentralized in terms of the degree of connectivity of our systems. So here again, centralized is where our homes and our buildings are all on one central sewage line. They go to one central treatment plant. Whereas a decentralized approach is where you have actually independent systems that operate independently of each other. But there's also some middle ground here. There are hybrid systems. And this, I would say, when we think about water reuse, is something that comes up over and over and over because most of our infrastructure right now is centralized. And so if we want to think about a way to achieve decentralized reuse, given our existing centralized infrastructure, one option would be to use something like a scalping plant. So this is where you basically take water from your sewer, bring it up, treat it, and use it locally, and then you can dump the solids or the things produced during that treatment process back into the collection line, and then those can be processed at a centralized facility. So this gives you kind of a balance between a centralized infrastructure that handles the solids associated with the wastewater, but then a decentralized water reuse option where you can use the treated water locally. And I would argue, and this is kind of what Gerald said, there's a lot of engineers and scientists who've worked for a long time to develop technologies to achieve really high quality water. So I would say we really do have the technologies to achieve water reuse. And these range from somewhat low-tech technologies like natural systems that you could, like constructed wetlands that you might be able to use in areas where you have more land availability, to very advanced treatment systems. And these also range in scale. So here I'm showing in the middle, this is one of the earlier, it was built in 2003, building scale water reuse projects in New York. It's located just outside Tribeca on the Lower West Side. They basically treat their wastewater in the basement of this apartment complex and use that treated water for flushing, for HVAC cooling, and for irrigation. And I think it only costs about $4,500 for a studio, so. And then we also have these projects. I'm showing here the Orange County Water District, which does indirect potable reuse. This is a large centralized facility. And here they treat wastewater to a very high standard. They use microfiltration and reverse osmosis. And then they do UV disinfection, and then they put it back into the ground, into their drinking water supply. So we have the technologies. And so what I think the conversation needs to be, and this relates to some of the previous conversations this morning, is what we really struggle with is implementing these in a way that is both socially, environmentally, and economically viable. And because these are very complex infrastructure systems where we have old infrastructure, new developments going up, a lot of different technology options at multiple different scales. These are complicated problems with lots of stakeholders involved and multiple criteria that need to be balanced. So I would say that this is really where we struggle when it comes to implementing these water reuse projects. So questions like, are we charging the right amount for water? Do we really, who bears the costs associated with this? How do we support regulations that enable water reuse? How do we develop more energy efficient technologies or more cost-effective technologies that are more likely to be implemented? So these are some of the questions that we really do struggle with. And so I'm just going to end with mentioning a couple of trade-offs that kind of illustrate some of these tensions that we have to balance when we're talking about water reuse projects. And so the first one is obviously it takes energy to treat and distribute water, okay? And that amount of energy that's required is largely a function of both the source water quality, but also the product water quality. And so if we compare, for example, doing water reuse using wastewater as our source water compared to desalination, in general, it's going to be a much less energy-intensive process. It's because it's very intensive to desalinate water because of those high salt concentrations. And then the second point I want to make just with this graph is just that depending on the water quality you're trying to achieve, you'll have different energy requirements. So it takes more energy to produce a higher quality water. So direct potable reuse is going to require a higher quality water than than a non-potable reuse system. And that's going to have an energy cost associated with it. So how well do we treat that water? We should be treating this idea of fit for purpose water is that we should be treating water for the purpose that it's needed for. And then the second trade-off that I'd like to highlight, and this is related to the scale and this centralization versus decentralization question, is really balancing energy and capital and operational costs associated with very distributed systems versus very centralized systems. So one thing we know is that smaller treatment systems in general require much more energy per volume of water treated. So you get economies of scale when you have really large treatment plants. I would say this is a huge reason why our infrastructure right now is very centralized. And this also goes with operational costs, right? You need less people to man a very large treatment plant per gallon of water treated than multiple small wastewater treatment plants across the city. But then you have to balance those treatment energy demands against the energy and the energy required for distributing and collecting that water. And so it costs more energy to distribute water over long distances. And so there's got to be a balance, and this is going to be very site-specific. Obviously, Houston's extremely flat, so topology matters here because pumping water uphill is a lot more energy intensive than pumping it over a long flat distance. But these distribution versus treatment energy and capital costs have to be balanced, and this has to be site-specific for every project that's being considered. I think I'm good. And so just to wrap up, what I'd like to just conclude with is the fact that we know these planned water reuse projects are on the rise, both across the U.S., across the world, and in Texas. We have the technologies. We have a lot of technologies. Obviously, there's a lot of development of new technologies still for water treatment and wastewater treatment and reuse. And this ranges from the very small-scale building systems to large-scale centralized systems. And what we really need is, I would argue, is more tools that aid decision makers and that really help in the implementation of these projects at a systems level. And kind of for the afternoon session, for those who are going to be sticking around, what I really hope that we'll get to discussing is what's the future of Houston, and what does the future of water reuse look like in Houston, given some of our specific context, specific constraints related to water and wastewater treatment. So thank you.
The next speaker is Tom Pankratz. He's a Houston-based independent consultant and the editor of Global Water Intelligence Weekly Water Desalination Report. He served as an expert advisor on some of the world's largest and most technically advanced water projects, has been appointed to serve on committees by the National Academy of Science, World Health Organization, Middle East Desal Research Center, and Australia's Nation Center of Excellence in Desalination. Tom is also former vice president of Secht Hill. And here at the Rice University, he's on the advisory board of the Newt Science Group. Welcome, Tom.
Thank you, Gerald. Well, it's a pleasure to be here, and I'd like to start by just reinforcing one of the points that Lauren just made, and that's when we're looking for a way to treat water, we've got to design it fit for purpose. When we think that a lot of the very pure drinking water that's delivered to your homes is simply used to convey wastewater back to a wastewater plant, it puts things in perspective. Quite a waste of good, high-quality water. So that's one point. And another point, I'm just mentioning these before I forget them, as a corollary to her presentation as far as reuse, is that when we're thinking about reuse and as far as becoming squeamish, we should be more concerned with water's quality than its history. Because at the end of the day, you can take any water, whether it's produced water from the oil field, seawater, or wastewater, and you can treat it effectively so it's potable quality water. So that's another point that's very important to focus on. What I'm going to talk about today is some of the challenges in getting new technology into the field and treating water. One of the things I do is I write about new technologies quite frequently, and universities can be one of the contributors to some of the hyperbole that exists, at least not necessarily the researchers, but the press departments, when they take this little good idea that's been proven in the lab on a bench scale and put out a blast of press release. It makes it look like water's going to miraculously be treated with no energy requirement. So I regularly look at these new technologies and try to put a reality coefficient on them, because to take a technology from the lab into the field and test it and then pass the regulatory approval process takes years. And no matter how good a new technology is, the likelihood that it's going to be implemented at one of the Houston treatment plants for broad-based use in a large community is going to be a slow process, slow, timely, and expensive process. So with that preface, I'll get into a little bit more the presentation itself that I intend to make. And when I first entered the water industry in the 1970s, the whole industry the technologies, the techniques for treating water was based primarily on Stokes' law. Now, this is a very simple equation that says that if you take a contaminant or a small particle and you coagulate them or bring them together into a larger particle, they'll settle. And the more effectively you can do that, the smaller the tank. But we've all seen these big circular or rectangular tanks that are the way we identify most water and wastewater treatment plants. They're designed so that they have enough detention time, so you hold the particles long enough so they'll settle to the bottom and allow gravity to do the separation so you can then remove it. Very effective and cost effective, but it takes a lot of footprint, and little things can happen in the process that prevents those particles from agglomerating and settling to the bottom. Now, another thing that happens is the ones that do make it out of the clarifier, or the settling basin, is you've got to filter those. And the bigger the particle is, the more effective it is at filtration, or the more easier it is to filter out. So this is the way most treatment plants are set up, and wastewater treatment plants as well, because what you're doing there is you're letting the bacteria use the organic matter in the waste as a food source so that they grow. They live their happy little lives eating other wastewater and growing big enough so that they will then settle. So again, Stokes' law enters in there. So since I got involved in the industry, Stokes' law still plays a factor, but all of the new technologies that we see really is designed to overcome Stokes' law or to defeat it, to have whatever treatment process you're trying to employ happen more quickly, happen in a smaller footprint, and more effectively. So you still want to build those bigger particles, but you want to do it quicker, you want to speed up the process, and you want to make sure that you get a complete removal. And that's where one of the biggest innovations in water and wastewater treatment technology has come into play in the last, it's an old technology. It's actually reverse osmosis membranes were patented in 1960. Microfiltration and ultrafiltration, which Lauren mentioned in the reuse processes, were both developed and commercialized in the 1960s. But it really took a long time before they made it into the mainstream. And I contend that in the last 15 years, they are the mainstream. They are now the predominant treatment technologies, or they're at least considered in every new plant, if not incorporated in the new plants. So the membrane is a pretty impressive thing. It's a barrier. It's a barrier that prevents, so even if some of those particles don't settle out like they were supposed to, or if they find their way through the filter, they still will be prevented from getting onto the next unit process. And the tighter the barrier, there's so many membranes available now that you size them based on your specific application. In some cases, you're just trying to get out the suspended solids or clay and the stuff in the river or groundwater. pretty easy to develop a low-pressure membrane, uses relatively little energy to effectively accomplish that, and to remove all particulates greater than 0.05 microns, or in some cases even less. The next step is a reverse osmosis membrane. And these are membranes that they look like saran wrap almost. I mean, they're so fine they seem solid, but yet the water will, under pressure, will pass through the membrane faster than the salts. So if you pump it under sufficient pressure, you'll pump the water through, the salts will stay behind, and you'll keep removing those as they accumulate. So these two processes have been employed in water and wastewater treatment plants around the world and throughout Texas. So but even with those technologies that seem to offer so much, I mean, when I first saw the MF membrane in 1980, I thought, well, the industry is going to look completely different. Well, it took 20 years before they really made the impact that I thought they should make. But often, as with the floods that we've just had in Houston, it takes a crisis. And one of the crises that really helped promote the use of membranes was the Milwaukee cryptosporidium outbreak in 1992, I think it was. 1992, 400,000 people were affected by the runoff from the Dairylands cattle fields. The cows grazed, their waste was washed into the rivers. It didn't settle like it should have. It didn't filter like it should have, and these little particles made it through into the drinking water. 400,000 people were contaminated. That immediately changed the landscape for filtration. There were similar instances in France, and they took a look at, they developed new rules that have been implemented to not only, in many cases, result in the use of membranes, but also to increase the performance of the sand filters. Sand filters are perfectly good treatment options when they're used effectively. But the contamination that occurred in Milwaukee demonstrated how devastating it can be if its treatment isn't accomplished properly. So this was a big turning point. Another turning point in water supply issues, we've heard about the reuse, and so I'm going to skip over that, and we'll hear more about reuse also. But the droughts that we've seen around the world have led to a real increased interest in desalination as a water supply. This is not a main topic of this conference, but I just want to mention that when you talk about desalination, it's a very broad subject. Most people consider desalination to be the removal of salt from seawater. But when it comes right down to it, in Texas, we've got 7.5 billion acre feet, I think it is, or I can't remember. It's some staggering amount of brackish water. This is water that's slightly too salty to drink, but several times less than salt concentration than seawater. So there's some real efforts underway within Texas to identify those brackish water resources, because they are in fact resources, to figure out how small utilities can, in following a decentralized approach, rather than building a monstrous billions-dollar desal plant, build a small community plant that serves a much smaller area. They're doing it in Cinco Ranch right now. They're building a small brackish water desalination plant, and there's several hundred of them around the state. But this is another technology that's, it's new emerging technologies. And believe it or not, the state of Texas still has guidelines for emerging technologies, and they consider desalination to be one of them that require pilot testing. Now, I'm not saying that it's not good to be cautious, because when it comes to public health, that's the number one criteria. But this is a process that was developed in 1960. The largest desalination plant the largest reverse osmosis desalination plant in the world was built in Dallas, Texas, for Texas Instruments in 1969. So it's a technology that we're pretty familiar with and has a lot to offer. Not only will it keep out the pathogens that we're worried about contaminating us, but also the salt, and also the other emerging contaminants that we'll be, I'm sure, hearing more about. Endocrine disruptors, the other pharmaceuticals get in the water. So there's a lot of new technologies out there, a lot of interesting technologies. it would be great to shorten the cycle, but shortening the development cycle, the research, the testing, and the regulatory cycle is something that is likely going to continue to be a long process, and a lot of this is already underway at places like Rice here. I mean, the Newt Center is looking at nanoparticles and how can we improve the performance of existing membrane technologies and also use renewable energies like solar energy to help drive the process. So a lot of interesting stuff going on. But it's a long, slow process, and for my sake, my kids' sake, my grandkids' sake, I'm glad it's a long, slow, deliberate process that we pay attention to the public health in the process. Thank you.
Our next speaker is Eva Stienle-Darling. She's the Vice President of the Water Reuse Organization of Texas, and she's the Principal Technologist of Carollo Engineering in Austin. Eva is an environmental engineer with 8 years of experience specializing in advanced treatment for water reuse. Her work for Carollo focuses on water reuse, including research, planning, feasibility studies, and the design for potable and non-potable reuse projects. She is co-leading several of Carollo's water reuse research foundation projects on direct potable reuse and is the principal investigator of an ongoing water quality study on the nation's first operational direct potable reuse facility operated by the Colorado River Municipal Water District at Big Spring, Texas. Eva is also Vice President of Water Reuse Texas. Welcome.
Thank you for that introduction, and also for being one of the few people who can actually pronounce my last name. I appreciate that. My mother is German, and so a lot of people have trouble with the Stienle. Turns out Lauren and I have similar backgrounds, so some of our slides are going to be introducing a little bit of the same material, but hopefully in a little bit different way. I want to talk about potable reuse specifically, so narrowing in on the beneficial reuse of former wastewater for drinking water purposes, and a few comments on technology, and hopefully it'll spark some interest. I'm not going into an extensive narrative here, but I have a few points that I want to bring up and hopefully create a discussion out of them. So starting with, we're drinking what? And I think we already had that moment a minute ago, an introduction to potable reuse. So when we talk about reuse in the urban water cycle, really we're talking about a closed loop system. We have our surface water source. We treat it at a drinking water treatment facility. We have a community. The wastewater created by that community is treated by a water resource recovery facility, and then it may or may not undergo additional treatment, advanced treatment before being returned to the environment. And when it's done in a loop, of course, we call this potable reuse. And now in Texas, we have some specific rules, and if it is considered a water of state, if this puddle is a water of the state, then we call it, it falls under existing surface water and drinking water treatment rules, we call it indirect reuse. We kind of drop the potable component of that. If it's not, it's regulated under a specific regulatory paradigm that the TCEQ has to regulate projects on a case-by-case basis. There are no formal regulations for this, this type of project, but there have been several permitted on a case-by-case basis. Moving ahead, of course, there are also the aquifer replenishment alternatives, where instead of this being a puddle, it's a hole in the ground. Obviously, it's a little bit understatement. It's an aquifer drinking water source. And with advanced treatment, for example, El Paso has been doing that since the 80s, treating their treated effluent at their Fred Harvey water reclamation facility. And they basically have a wastewater treatment plant and then an enhanced water treatment plant on the end of that. And that's how the water is treated before it's put back into the ground to augment their drinking water supplies. Oh, there's the example. And then, of course, what do we mean when we talk about direct potable reuse? Well, direct potable reuse bypasses the environment, so we no longer have that lake or river or aquifer in the cycle. Instead, we're returning advanced treated water either directly to a drinking water facility at its intake, somewhere in the middle of the process, or even what's sometimes called finished water augmentation, where we are actually just introducing it directly into the distribution system. And of course, we need different levels of treatment for each of those scenarios. I wanted to show on a map what this might look like. So the only operating municipal scale direct potable reuse facility is in Big Spring, Texas, which is out in West Texas, about an hour east of the Midland-Odessa area. It's mostly an oil town, and if you've ever been to that part of the state, you know that there's no water to spare. And so approximately 15 years ago, the Colorado River Municipal Water District embarked on this project. It took them 10 years to get it permitted. And what I'm showing here is a creek, Beals Creek, some pipelines, one of them labeled as EV Spence. You can see the city of Big Spring. I don't know if this is a pointer or no, it's on. But I'll walk you through it, and you see a couple of boxes that I'm going to highlight. The first one here is the city's wastewater treatment plant. Adjacent to it, we have what they very aptly call a raw water production facility. Nobody's calling this toilet to tap. What we're doing is we're creating a raw water that is suitable for treatment along with all of their other surface waters in conventional water treatment plants. They have a very fortuitous situation where they can discharge the byproducts of this treatment process, which is kind of the Achilles heel of the fantastic RO process, reverse osmosis process. They can discharge that elevated salinity and also with some contaminants in it. But still, this is what they would normally discharge in the form of wastewater, treated wastewater, to Beals Creek, which is a saline creek with a background salinity level many times the drinking water level, almost as high as seawater. It's just the natural form of that creek. It's been diverted for many years from the area's water system because, of course, we don't want that highly saline water in our water supply, and so they have a built-in evaporation pond effectively for their waste stream in this system, which is a really fortuitous circumstance for that project. The product water is blended within the pipeline. You can see where that came up within their existing raw water distribution pipeline. Goes up and around. It mixes a little bit in what they call the base 5 reservoir, which is 15 million gallons. If you think at the municipal scale, that's almost nothing. It's kind of a wide spot in the pipe. And then some of that water is returned to the city of Big Spring to their water treatment plant. And so if you put the little arrow that indicates the flow of water through the community, you can see how that circle is completed in a pretty small geographic area. And that's really what makes this unique, and the lack of kind of an environmental step that we've historically relied on. So actually echoing the points that both Tom and Lauren have made already, I'm not even going to really talk much about treatment because I think the treatment options themselves are really well understood. We have a lot of treatment technologies in our toolbox, and it's really a question of the efficient application of those treatment processes. There are a few things that I'm going to highlight. So how do you meet our requirements for a treatment process like that? Well, the California model, as I like to call it, but it is really the kind of the gold standard, and that's what was applied at Big Spring as well, is a combination of these processes Tom introduced, microfiltration and reverse osmosis, with an additional step called advanced oxidation, which is a combination of UV light for pathogen kill and also some chemical added to remove additional chemical contaminants. However, it has a big Achilles heel, and we haven't really talked about that, but basically approximately 15% of the water is lost because it's a byproduct. It's the membrane separation creates a waste stream that also has to be disposed of. And often case, I sort of call it the tail that wags the dog, which is that disposal can often drive the cost of the facility, can often kill the project because there is no good way to dispose of that waste. So in certain cases where desalination, so removal of salts basically isn't needed, we have some alternatives. Reverse osmosis most often is replaced by a combination of ozone and biologically active carbon. So that's combining processes we've typically used in water treatment plants, but a little bit more firepower there. And instead of separating out the contaminants, we're destroying them via oxidation and then biological degradation. We follow that with the other processes we've already had, micro or ultrafiltration or UV and advanced oxidation, with some options to insert at will or as needed activated carbon or chlorine for additional disinfection. But I'd really, so one of the examples, okay, one more slide on process and then I can wake you all up again. One of our demonstration projects that I'm particularly excited about is a project that's been running for about a year in Altamont Springs, Florida, where we are proving the suitability of advanced treatment for potable reuse purposes without reverse osmosis. So you can see I've got a bunch of colored boxes with different acronyms in them, but none of those acronyms is RO. So we have the ozone, we have the BAF, which is a biologically active filter, we have some chemical addition, we have an ultrafilter, which is a lower pressure membrane, and the byproduct from that can be recycled to the head of the plant, so it's not a plant waste stream. We have a GAC, adsorption process, to catch any remaining organic constituents in the water, and then again this UV disinfection step that's really the belt to our suspenders to our belt. And in a full-scale system, we would add engineered storage as a way to address any potential water or process failure in this process, so that water that doesn't meet specifications doesn't get delivered to the customers directly, because that's one other concern you have when you're coupling a system so closely, is that you need to make sure that you have enough time to react to a process failure. So what do we need then if our treatment processes are well defined, other than money, of course, to implement those processes? There are a few things that we still are kind of looking for in the research realm, in the development realm, the I wish I had. The first one is what I like to call the magic meter. I would love a device that would tell me at the end of the pipe that this water meets all the standards that it needs to meet. And the problem is that we don't have that kind of a meter. We have laboratories that can confirm the absence of chemicals to orders of magnitude below concentrations that are of relevance to health. But we don't have that for pathogens. We don't have that for virus. We don't have that for Crypto and Giardia. That's not to say we don't have methods that measure them and measure them at very low levels, but the drinking water goals and in this country that are based on an accepted risk of infection would require us to filter 2 Olympic-sized swimming pools worth of water to confirm for one sample that we're meeting the goal for virus in drinking water. So we have some very stringent standards, and that's great. But we have to monitor our processes to make sure they are doing their jobs so that we can confirm that we are getting what we need out of our treatment processes. So one of the things I would love is better sensor technology, better monitoring technology for our existing processes that can confirm they are doing their treatment and getting the credit in the end with the regulators for the amount of treatment they are providing. That will allow us to lower the cost on treatment projects, because now the treatment that we know is occurring, we can confirm it at all times, and we don't have to build additional redundant treatment for it because we've eliminated that uncertainty. So surrogate monitoring here says the treatment was working as designed at each step. And this is what we already do. What I want is better sensors, better ways to confirm that that treatment is happening. Another topic that's really important, I think, and that has been overlooked to date is enhanced source control. So looking at, this is a picture of the collection system in Oxnard, California, and they are embarking on a potable reuse project. And you can see we're now focusing on where does our water come from? You know, in conventional water treatment, we protect our source waters. We say, no, you can't put waste, you can't dump stuff. Some places don't allow recreation. We need to look at our sewer systems and say, well, you know, that certified waste hauler, we don't really know what he's putting in there or she's putting in there. Maybe that waste should not be put into a collection system that is serving as a source water for drinking water. And then finally, operator training, and this is just to kick off a discussion. I don't want to go into detail. There are some efforts already underway, but especially for these advanced treatment processes, some of which, of course, are 50 years old, but we still consider them advanced. We need operator training and certification programs that will work in this nexus between the wastewater and water fields. And so I think with that, I think my time is up, but I think we'll have lots of time for discussion.
Thank you. Last but not least, I'd like to introduce Professor Desmond Lawyer. He's the Nasir Al-Rashid Chair in Civil Engineering at the University of Texas in Austin. He earned his PhD in Environmental Engineering from the University of North Carolina at Chapel Hill in 1980. He joined the faculty of the University of Texas in the same year. Mr. Lawyer was named a University Distinguished Teaching Professor in 1997. 1999, he received the AP Black Award for significant and sustained research contributions in drinking water from the American Water Works Association. The current focus of his work is on pretreatment for membrane processes, including the improvement of water recovery in desalination by reverse osmosis. Please, the stage is yours. Thank you.
So good morning, everybody. Thanks very much for coming. Mostly I'm going to talk about wastewater. How many wastewater engineers do we have in the audience here? We got a pocket over there in that corner. Okay. Okay, so if I can figure out how to forward this thing, I'll be in good shape. There we go. So we've actually already talked about this terminology, so I'm going to skip through this rather quickly. Potable reuse of water, transforming wastewater into drinking water. Lauren already talked about de facto reuse, where we're using a water supply that has made up in whole or part of treated wastewater. And then we have indirect potable reuse, where we take the water from a wastewater treatment plant, put it through some sort of advanced treatment, and then put it into an environmental buffer, another term that's been used a few times already by the panel. And then eventually we pull it back out. And then lastly, we have direct potable reuse, which I think is the primary subject of interest here this morning. And it's similar to indirect potable reuse, but we have no environmental buffer. That is to say, the water stays within engineered systems from toilet to tap. And this is something that, has, I think the word squeamish was used earlier, but the fact is that this is something that is now a fact of life in a few places and is likely to become a fact of life in a lot more. What are the concerns about this? Well, the first concerns, of course, are pathogens. When you're supplying drinking water, protecting the public health is your one and only job, basically. So removing pathogens so people don't get sick tomorrow is critical. We talk about this in terms of log removals of viruses, Cryptosporidium and Giardia. Emerging contaminants are of importance to us, so-called pharmaceuticals and personal care products, endocrine disrupting compounds. These are terms that are used in our field to describe some contaminants that are not generally treated very well in wastewater, and so if we're going to do direct potable reuse, we have to make sure that our technology takes care of these things. In a lot of cases, we don't know the health effects, but certainly the public concern is great. There's all kinds of cartoons you can find about pharmaceuticals and personal care products coming out your tap water. Organic matter and disinfection byproducts, this has been a huge driver of drinking water treatment for my entire career. I started graduate school in 1974, and that fall, the first article about disinfection byproducts in the drinking waters came out, and it's been like a huge driver of drinking water treatment ever since. But effluent-derived organic matter, that is to say, what's in wastewater effluent, is different than natural organic matter. And we probably don't know nearly as much about it and how it is dealt with in treatment processes as we need to know. And then, of course, there's a lot of inorganics of concern. I list a few here: ammonia, nitrite, and nitrate. Certainly metals fall into this category, and we need to make sure these are handled well in treatment processes if we're going to do direct potable reuse. So there was a project by the Texas Water Development Board, big project as it turned out. The funding from that was supplemented by a number of cities, including Houston, and it was overseen by Alan Plummer and Associates, a Texas-based water and wastewater treatment firm. And there was in their report, which is available from the Texas Water Development Board, they have a whole lot of different possible treatment trains. And I'm just going to run through a few. The first one, I'm calling it here perhaps the gold standard. You have secondary or tertiary wastewater treatment. You have, this is very similar to what Eva was just talking about. You have ozone, you have micro or ultrafiltration, you have reverse osmosis, you have advanced oxidation processes, and you have some sort of stabilization process, which turns out to mean that you add some minerals back into the water because you make it so clean that it will corrode your pipes if you don't do that. Then you have some sort of storage, and finally it goes to a water treatment plant as if it wasn't clean enough to drink, although it probably is. I'm just going to run through a couple of these things. Again, wastewater treatment with membrane bioreactor and achieving full nitrification, so you've oxidized all the ammonia to nitrate. Then you go to reverse osmosis, and the rest of it is pretty similar to what I had before. But what a membrane bioreactor does is it makes the effluent quality from the wastewater treatment plant almost particle-free, and if you've achieved nitrification, then you've taken care of the possibility of an ammonia problem. Another one, again, you have wastewater treatment plant, including disinfection. So you've hopefully gotten rid of a lot of microorganisms. Again, you have micro or ultrafiltration to get rid of particles. This is, Tom mentioned this in his talk. Ozone, again, for oxidation and perhaps disinfection. Biologically activated carbon, which almost always follows ozone because you've broken large molecules into smaller molecules that now microbes can effectively use as food source. You disinfect with chlorine. Again, you have a storage unit and a water treatment plant, which they consider not optional in this case because you have not made the water clean enough to drink. So, and then lastly, I was on a kind of a review board for the El Paso system as they were considering designing or instituting a direct potable reuse system. This would be the first system made in the U.S. if they do it the way they were talking about at the time a couple of years ago, that had no water treatment plant afterwards. Basically, you take the water from this advanced treatment process and put it directly into the distribution system of the drinking water supply. And their process had secondary wastewater treatment, including nitrification. They thought about putting in denitrification filters to take that nitrate and make it into nitrogen gas, which would go out in the atmosphere. They considered that in the treatment process train in the pilot plant, but they eliminated it in the end. Ozone was also piloted, but abandoned, at least in the pilot plant, due to problems that happened during that. And of course, they wanted disinfection with chlorine or chloramines to prevent membrane biofouling, and then have the membranes, the micro or ultrafiltration to remove particles. Nanofiltration they considered, but they ended up going with reverse osmosis, which is a tighter membrane, to remove both organics and inorganics. Then an advanced oxidation process and carbon filtration. So again, these are lots of treatment processes, one after the other in here. My opinion, I'm just going to talk about this here for a few minutes, is that most of the conversation in the field about direct potable reuse has been conceived as a three-part process. One, you have conventional wastewater treatment, at least secondary treatment. Second, you have an advanced treatment process, the kinds of things that a few of us have been talking about, advanced oxidation processes and typically reverse osmosis. And then you have conventional drinking water treatment plant. And most of the work that's been done in our field about this has started with step 2. And my point this morning is that we should start with step 1. That is to say, we should think about what we're doing in the wastewater treatment plant first, because if it's going to end up as drinking water, we need to know what's going on there. And so I have 4 ideas. We can talk about these in detail later, perhaps. But the first is to change the influent characteristics. That is to say, of the wastewater treatment plant, not of the advanced treatment process. And Eva just mentioned this, having an extensive industrial pretreatment program is important, but I think we also have to have the public involved in this. Every single household should be conscious of the fact that their wastewater is going to end up as drinking water, and we should have a public education system and a pollution prevention program to prevent some things from getting into the wastewater, like drugs, for example, that are not treated very well in most conventional wastewater treatment plants. We should do extensive flow equalization. Flow equalization is used in wastewater treatment plants commonly, so that because, every day there's higher flows at 10 o'clock in the morning than there are at 2 o'clock in the morning, and so you want to even out that flow somewhat. But we don't do it in a really extensive way, and as a result, we don't treat wastewater nearly as well as we could if we had much more dramatic flow equalization. We should replace conventional primary treatment with micro or ultrafiltration. This is Tom's point about Stokes' law. Stokes' law works by conventional primary treatment, settling particles out. We could get rid of particles way, way better if we used ultrafiltration at that stage, or microfiltration. And it might be a little bit more expensive, but it would do a much better job. And then what that would do is it would free up the biological treatment to just deal with soluble materials instead of trying to break up particulate matter. And lastly, I believe, and this is, some people would not agree with me on this, is that not only should we do nitrification, but we should do denitrification. I believe we should not rely on reverse osmosis to get rid of the nitrogen compounds. It's not to say that they're not capable of doing it, but one of the philosophies of drinking water treatment for the last 75, 100 years has been to have multiple barriers so that if anything goes wrong, you're not relying on just a single system to do that. And if we don't do nitrification and denitrification in our wastewater treatment plants, which is a very known and doable technology, then we're going to rely on RO only to get rid of nitrate. Nitrate is, not a good thing, especially for young babies. And I don't think we should take the public health risk of having that by only having a single barrier. Those are my thoughts. Look forward to the conversation.
We have a few minutes for Q&A. Please state your name and kindly and your affiliation.
Yes, Jim Tucker, resident and geologist. Thank you for the panel for reminding us there is no new water outside of a little volcanic contribution, which is very minor, but we only have the water we've got and have to figure out what we do with it. Since it appears to the amateur to be downscalable, would effective residential gray water reuse allow the facilities that we've heard described this morning to focus really on the treatment of the organic and inorganic volumes without having the conventional wastewater stream that's everything that comes at least out of households and a lot of commercial businesses?
I think, is this on? Can you hear me? I guess, oh, here we go. Now it's on. I think the simple answer is yes, that would work. The more complicated answer is that part of the challenges, and our moderator mentioned this in just a aside earlier, is that if we drastically cut down on wastewater flows in existing collection systems, we've created another problem, which is that we no longer have enough flow to push the solids through what are now vastly oversized pipes. So that's a big consideration. And in all of this, one of the things I wanted to mention, which all of us who talk about treatment get excited about the bells and whistles and shiny objects, is the one biggest killer of water projects is usually the cost of transporting the water. And so it's the distance, it's the distribution. So for a purple pipe project, as we call them, so the non-potable reuse projects, well, what do you have to do? It's great to have a fit-for-purpose water, and I agree that we should have water quality that meets the end goal, but you can only take that so far if you're having to rip up all the streets of Houston to put in another distribution system paralleling all of your other wastewater collection, water distribution, all of your other utilities. Those streets get clogged up pretty fast. So I think in concept, yes. And I think as we gradually adopt that sort of mindset, I think there will be that there's a place for that. But like anything else that's disruptive, it's going to disrupt some things, and so we need to be cognizant of them.
Thank you. Please.
My name is Hongbo Du from Prairie View A&M University. We are working on the forward osmosis membrane filtration for the produced water treatment. I want to ask the question, in this session, there is no discussion about the produced water treatment with advanced membrane technologies, for example, forward osmosis or even the membrane distillation. I want to ask, how about the future of the forward osmosis? We know generally the forward osmosis can reach the similar quality of the water as the reverse osmosis. But the problem is the flux is a little bit lower. That is the question I want to ask. How about the future of the forward osmosis?
Well, forward osmosis is a very interesting technology, and for those of you who aren't familiar with it, reverse osmosis means that you're applying a pressure greater than the osmotic pressure to push water through that membrane. Forward osmosis is what happens in nature. It's how a tree gets water, because I always need a chalkboard when I try to describe it, but it's what happens in nature, and it doesn't require pumping. But as with all of the processes we've talked about today, there are trade-offs. Reverse osmosis is great, but it produces a brine, and so on and so forth. It takes more energy. Forward osmosis is great, but I think the complications with forward osmosis are too detailed to go into at this presentation. My personal feeling is forward osmosis has a lot of application in industrial processes, primarily in dealing with high salinity waters. I don't think it will ever replace or ever be a drinking water, a mainstream drinking water treatment process. So we'll stop there, because we could talk about this for the rest of the day.
Thank you. Please.
Hi, my name is Emily Wen. I am a student studying civil and environmental engineering, and most importantly, I just finished an internship at a wastewater treatment plant trying to reduce their energy usage because it was a very large burden on them to try to meet the standards and not have to exceed the budget that they had. So my question is, for Texas, are the standards that are in place suitable for the health, and do you predict that they will put in more stringent standards, and if so, how will they compensate for that extra energy consumption that will occur?
Can we convene another workshop to discuss this?
I think that the standards that are in place generally are sufficient, but I do think there's going to be more standards coming down the road. I mean, for example, and the way the EPA works, they have this so-called candidate contaminant list that they have to kind of keep up and decide whether new chemicals need to be, or more chemicals need to be directly regulated for drinking water. The process is so cumbersome that it's difficult for them to ever get a new regulation. But I do think the public is going to demand higher quality water in time, and so I do expect that the regulations will increase. And we might have to save our energy someplace else.
Eva has a short comment.
Yeah, I think the other thing to keep in mind is, even if the standards don't change, the fact that the state is growing and the country is growing, we're increasing not just in absolute population, but in population density. And so as we densify the cycles, we're going to have to, the assimilative capacity of the natural systems is only so big. And so the more people there are, to keep the same load of pollutants that we do find acceptable now, the concentration limits are going to have to reduce, and there'll have to be more work on both carbon and nitrogen loading to the receiving water bodies.
Thank you. Andy?
Hi, Gerald. Andy Shaw with Black & Veatch again. Lauren, I had a question for you. Several years ago, at an IWA conference where they were talking about centralized versus decentralized, and at the time they were fascinated by this idea of a cluster-based approach. And as they described it, it's like, okay, lots of little communities with their own treatment plant. I'm like, wait a minute, that's the mud system in Houston. Or is the problem we have now, Houston's got 40 little plants, mostly smaller plants, not big centralized plants. So as we're having some discussions about flooding, and it's better to maybe centralize some of that and shut down plants, in terms of reuse, actually, there's an opportunity maybe here that we're not using yet. I don't know if you have any thoughts or comments on that.
Yeah, I'm really glad you brought that up. So we're actively collaborating with the city to try and address that very specific question. So like the previous panel said, there's 40 wastewater treatment plants in Houston. About 20 of them are quite small, so less than 2 MGD. And right now the plans for the city are to consolidate. So they're looking at a lot of their very old package plants that are 1 MGD, 1.5 MGD, and planning right now to consolidate 3 to 4 to 5 of these to one larger facility. So they only have to upgrade one facility as opposed to upgrade all of these smaller package plants. And the idea is that both that's more cost effective and that there's going to be savings in terms of operators, right? Because it's less people to man those plants. Mm-hmm. But so that's the question we've asked them is, have they considered water reuse in that at all? And I don't think, I think they have, but I don't think they have to the extent that they're really planning for a lot of water reuse. So they have some very specific areas within the city that they want to look at doing non-potable reuse. So basically irrigation for golf courses, irrigation for parks, and they're trying to think about the location of these consolidated plants in order to accommodate that as a potential future indirect non-potable reuse. Sorry, I said that incorrectly. Non-potable reuse applications. Right. But I agree. I think that this decentralized system that Houston currently has actually could be a potential model if they were really trying to be very forward-thinking for thinking about more decentralized water treatment for reuse.
Cool.
Thank you. Last gentleman.
My name's Kim King. I've got 2 questions for you. One has to do with the desalination. When the weatherman says the amount of rain filled up 3,000 astronomes, that doesn't really give me a picture. But when he says that that's the amount of water that goes over Niagara for 15 days, I've got a kind of picture of that. I've always tried to equate desalination to how many barrels of oil does it take, or how many gallons of oil does it take to produce a gallon of water through desalination? And when you tell me it's kilowatts per cubic meter, but I don't have a picture of that. But if you tell me it's a gallon of oil per a gallon of water, I can visualize what that means.
How about BTUs per acre foot? Stop that.
And the other question is that I've heard you comment that, all right, we're throwing all of our chemicals and drugs and whatever in the water system. But I haven't heard you say we've got a good method of getting rid of those as part of the process. That's kind of what the message is I think you've been left with.
Well, we've got a good method for getting rid of them. It's again, we're kind of limited here, and you asked some complicated questions. As we heard, doesn't say there are ways to treat those organics and to destroy them, oxidize them. But as far as desalination, how much oil does it take? It generally takes, to do 1,000 gallons, it takes about 13 to 15 kilowatt hours. I don't know how to turn that into a barrel of oil quickly without doing the calculations, but it's 5 or 6 times more expensive than conventional water. 60% of the cost of desalinated water is usually energy, and it's the most expensive way to get drinking water, and that's why you look at everything else first. But at the end of the day, and I'm talking about seawater, when we're talking about brackish water, like I mentioned they do at Cinco Ranch, it's much more in line with the conventional treatment processes because there's a lot less salt. So you've asked some good questions. Those are questions that desalters wrestle with every day, trying to bring down the cost of energy. But also, when you see some of these press releases that claim that they can operate a desal plant 1,000 times more efficiently, don't believe them. we're about as low as we're going to get. We're within 25% of the theoretical minimum energy of separation. So you just cannot get much lower. The changes that we see, in my personal opinion, through all of these treatment technologies we talked about today are generally incremental. We're going to see moving the needle a little bit at a time. We're going to figure out new ways of doing things. Even the gentleman's question about measuring these, or the quality of water, I've seen some things in the last couple months that have amazed me, and that is, one is next generation sequencing, which is DNA sequencing of treated water at the end of the pipe, and you can see everything that's in it, and you can detect exactly where it came from. And they're doing that right now at Orange County at one of the plants that was shown on one of the slides. So they're able to sequence the genes in the wastewater, and they can do it overnight for $100, $150. So as we get closer to doing that real time, we'll get a much better idea of what the quality of water is. It'll help us design treatment plants better, and we'll be able to see exactly what's going on. But these are incremental steps we're taking, and a lot of research is going on behind the scenes, and really interesting stuff.
Well, thank you, everybody. And here I pass it on to Linda.
Okay. So I'd just like to add one last comment, and this was the second to last question around decentralization and centralization, and comment that as we were sitting with the City of Houston and we were talking about forming this conference, Lauren from the engineering department, myself from the Baker Institute, we were hearing about the plans to centralize, and we said we really need to get a better understanding to the City of Houston as to what the advantages are of decentralized systems. And that became a big theme of these conversations and is the theme of one of the workshops. So we are actively, let's say, preparing a conversation to help inform the city to think about the advantages that might be involved in having so many treatment systems and seeing if we can have an effect on some of the decisions going forward. So this is how these kinds of conferences and workshops really can influence what happens going forward into the future. And with that, I want to thank this panel, and I want to thank everybody for attending and those who are live streaming. For those of you that are interested in, let's say, reviewing some of the tapes, in about 24 or 48 hours, all of these presentations will be loaded up to the webpage so that you may be able to listen to them again or have your friends listen to them or review pieces that were important to you. Again, there are refreshments out in the entryway if you'd like to continue the conversation, and I thank everybody for their participation.